Hi guys, in this video we are going to talk about the effect of temperature. If we have a member and this member is supported from one end and free from the other end and is subjected to change of temperature, even if it's increase or decrease, rise or drop in temperature, but we have a change in temperature. So the length, the original length of this member will be changed. If we have increase in temperature, we will have elongation with delta T due to temperature. If we have drop in temperature, we will have contraction, delta T. How much is this contraction or this elongation due to the change of temperature? Equal alpha delta T time L. Alpha is a constant. It's called linear coefficient of thermal expansion based on the material type. Delta T is the change in temperature. Be careful, the change in temperature. And the L is the original length of the member. So just to remind you what we learned so far in this chapter. If we have a member supported from one end and under the effect of a force P, we should expect elongation or contraction or a change in the length, axial deformation equal P L divided by A E. If this member under the effect of a change of temperature delta T, we will have axial deformation, elongation or contraction, delta T equal alpha delta T time L. Alpha is the thermal coefficient, coefficient of thermal expansion. Coefficient of thermal expansion. Delta T is the change in temperature. L is the length of the member. Does that make sense? If we prevented the expansion or contraction due to temperature, we will have stress. And the amount of stress depends on, did you completely prevented the expansion and the contraction? In this case, your stress will be alpha delta T time E, Young's modulus. But if you partially prevented the thermal expansion or the thermal contraction, we will have stress, but due to the amount you prevented. How can I explain this one? I don't recommend you this expression, but I have a different technique how to figure out the thermal stress. If we have a change in temperature, we should expect stress. We should expect stress only if you prevented the axial deformation. If you prevented completely or partially the axial deformation, but we have prevention. We have prevention for the axial deformation due to temperature. In this case, we will have thermal stress. Delta T, I'm sorry, sigma T, axial thermal stress. So I would like to repeat this point one more time. If we have a member supported from one end and free from the other end, in this case, and we have a change in temperature, in this case, we will have axial deformation equal alpha delta T time L. And the stress in this case will be zero. Why? Because I did not prevent the axial deformation due to change of temperature. But if this member is supported from this end and prevented from the other end also with another wall, or we have a gap between the end of the second end of the member, and after a change of temperature, the elongation of this one will hit the wall, would like to try to expand more, but the wall will prevent. So in this case, your stress due to temperature will have a value. How much is this value? We will discuss this in the following two examples. But we have stress, we have thermal stress due to change of temperature because because I prevented the axial deformation. In the first one, I completely prevented the axial deformation. In the second one, I partially prevented the axial deformation. So both of them, by the end, we prevented something. So we will have thermal stress. But if you did not, if it's free to expand, if it's free to contract, we will not have any stress. This is very important. In the first example, we are given a rod or member supported between two walls, wall number one and wall number two. And this bar of aluminum is under the effect of increase in temperature. So delta T increase in temperature equal 100 Fahrenheit. The diameter of this bar will give you the area, cross-section area by divide 4 times this diameter square will be 0.785 inches square. And the length of this bar equal 3 feet, which equal 3 times 12 will be 36 inch. So how to solve this kind of problem? We are looking to figure out what is the normal stress and what are the reactions at the two walls. This kind of problem will be solved like this. I will assume this bar is free from this end and supported from the other end. So this one is free right now. Just assume. In this case, under the effect of the change of temperature 100 Fahrenheit, we should expect expansion with value delta T. Does that make sense? We assumed this bar is supported from one end and free from the other end. So it's free to expand. How much is this expansion? According to the axial deformation due to temperature equal alpha delta T change in temperature time L. Alpha, which is the coefficient of thermal expansion, is given 12.8 times 10 to power negative 6. It's given here. The change of temperature is 100 Fahrenheit. The original length of this member 3 feet, which is 36 inch. So the expected free expansion will be 0.7 0.046 inch. However, the member is not free to expand. So this expand, which is 0.046 inch, is not free. So we have a wall at this end. So I will assume that this wall will apply a force P. This force P trying to push this part of expansion back. So this expansion or this amount of axial deformation will be pushed back by a force P subjected by the wall that I assumed it's not existing in the first step. So in this case, this force P will cause axial deformation PLAE, and this axial deformation will equivalent to the prevented amount of axial deformation 0.046 inch. Does that make sense? So I solved this problem with two steps. The first step, I assumed that the member is supported from one wall and free from the other wall. So it will expand freely. How much? 0.046 inch. But this is not the case. We have here a wall. This wall will prevent any expansion. So I will assume I have a force. This force will be applied by the existing wall, and this force will return the expansion or will return the axial deformation back. So this force will apply axial deformation PL divided by AE equal 0.046. So right now, P, I don't know. What is the length of the member? 36 inch. A, what is the cross-section area of the member? 0.785. What is the Young's modulus of the material? The Young's modulus is not given, but it should be given. E, we can assume it. E equal, we can assume it, how much for aluminum? I cannot remember. Is it here? No. So we can assume it like maybe 15,000 PSI. The E, Young's modulus of aluminum, we can assume it should be given. I'm sorry, it should be given. So the E equal 15,000 PSI. This PLAE must equal the prevented elongation 0.046 inch. So looks like everything in inch, and this one will be in kib. So I can figure out the applied force P. This applied force will be 15 kib. So I converted my problem from thermal problem to a force problem. So I have a reaction here in this wall, P equal 15 kib. If you apply summation f of x equals 0, we must have here another 15 kib. These are the two reactions in the two walls. Wall number 1 and wall number 2. Also, I can say the stress equal the applied force 15 kib divided by the cross-section area 0.85. So it will be negative 19.1 KSI, negative. Why? Because it's a compression. This one is compression, this one is compression. Actually, this is the thermal stress. You will ask me, hey, this stress is coming from applied force. Okay, but this applied force is coming from what? Is coming from the axial deformation due to temperature. So this reaction is related to the axial deformation which was prevented by the walls. So it's indirect stress. Yes, it's calculated from the axial force P, which equal 15, but this P15 is coming from the axial deformation, which is coming from the temperature. So this is the thermal stress due to the effect of temperature. That makes sense? So this technique is better than using this expression. I don't recommend it to use this expression because sometimes we are not completely prevent the deformation or the axial deformation. Sometimes we have partially prevention. So I do recommend to do like this. First step, assume your member is free from one end. Then the existing wall will prevent this elongation with applying a force. This force trying to push the whole amount of elongation back. So PL divided by EE will equal 0.046. Let's see the next example. We have the same rod, but with a gap between the free end and this wall. This gap equal 0.01 inch. So can you tell me what is the stress in the bar and what are the reactions in the two walls? Exactly like the previous example, but the only difference between this example and this example, in this one we don't have, in this one we have a gap between the end of the bar and the wall. In this one we don't have. So let's see what will be the difference. I will solve it with the same technique. First, I'm gonna assume the bar is free from one end, completely free. Even I don't have any other wall, only one wall from this side, nothing else. So under the change of temperature delta T equal 100 Fahrenheit, this bar will expand freely. How much? Delta T. This amount of thermal axial deformation equal alpha delta T time L. Alpha equal 12.8 time 10 to power negative 6. Change of temperature 100. The original length was 3 feet. I'm gonna multiply it by 12 to be an inch. So the free elongation will be 0.046 inch. Step number 2. We have a wall will prevent, but the wall will not prevent the whole elongation. Be careful. Be careful. Right now, we have this elongation which was free. How much? 0.046 inch. But the existing wall is here. This wall will apply a force P to prevent this amount of elongation only. So the applied force P will prevent only 0.046 minus 0.01. So will prevent how much? 0.036 inch. because this part of the elongation can happen, but any other elongation will not be happen, will be prevented by this wall. So in this case, we have partially prevention, not the whole amount of elongation is prevented. So the PL divided by AE, which will be prevented by this applied force, will equal 0.036 after you subtract the available gap. Does that make sense? So we are solving the problem in the same technique. But in this case, we have partially prevention for the elongation, not the whole elongation is prevented. So I can say the applied force P, I don't know how much. The elongation is 3 feet by 12 to be an inch. The cross-section area 0.785. The youngest modulus is 15,000 PSI, equal 0.036 inch. The only unknown is the value of the P, 0.785 times 15,000 times 0.036 divided by 36. So the amount of value will be 11.8 kip. So the reactions on this wall will be 11.8 kip. On this wall, for summation f of x will be also 11.8 kip. So the thermal stress will be 11.8 kip divided by 0.785 will give you negative because it's a compression. 15 psi. That makes sense? This is how to solve the effect of temperature on a member. Keep in your mind, if you I will solve this kind of problem by these two steps. The first step, I will assume we have free expansion. How much? Alpha delta TL. Then you have a support, you have a wall preventing this total amount of expansion. So we'll apply a force P, will prevent this expansion. Or sometimes the wall will prevent part of this expansion, not the whole expansion, based on if you have a gap or not.